Planets form in the disks that surround young stars, so-called protoplanetary disks. These disks usually last between 5 and 10 million years. Astronomers think that the transition from a young star with a disk to a young star without a disk happens very fast because they see very few stars in this transition phase. The study of such transition disks is very important for understanding the mechanisms responsible for disk dissipation. What impact could young forming planets have on these disks? Let's ask Andres Carmona, an astronomer who investigates these transition disks.
So, could you tell me what a transition disk is?
Well, to understand what a transition disk is, first we need to understand how astronomers figure out that objects have disks. So here in this image that I have here, I display something called the spectral energy distribution. That is a very simple plot on which we plot the flux of the star as a function of the color. So a star will emit some light in the blue, some light in the red, and if you are a star like the sun, you're going to emit a lot of light in the green and in the yellow that is in this part here. So when astronomers observe star-forming regions, they find something very interesting. They find that some objects, many of them, they have something called the infrared excess. That is simply that at infrared wavelengths, they have a strong emission. And from where comes this emission? Well, this emission is related to the presence of the dust particles in the disk. So the star shines, the dust particles get warm, and they will remit this light in the infrared. And because we have lots of dust particles, we will have a strong infrared excess. Now, when astronomers observe these star-forming regions, they find two kinds of objects. They find the objects that they have no disks because they don't have infrared excess, and they find the objects that have infrared excess, thus they have disks. Now, but there are a few weirdos that they have very special spectral energy distributions, and these are what we call the transition disks. To understand that, we need to get back to what we observe in a spectral energy distribution. So, if you are in a disk, if you are close to the star, you will be hot. If you are further away, you will be cold. So, in a spectral energy distribution, we observe the contributions of the hot material in the near infrared, the warm material in the mid-infrared, and the cold material far away in the millimeter wavelength regime. Now, if we have a spectral energy distribution of a transition disk, that is this one that I have here, essentially what we have is that there is a lack of emission of hot material, lack of emission of hot dust, and we think that is related to the presence of a gap in the dust distribution. And in the image that I showed there is an image taken with the SMA telescope in Hawaii. We see clearly the evidence of the gap in a disk.
So what produces these gaps in the disk then?
Well, there is an additional very interesting story, is that in those gaps we know there is gas. And in this image that I show from the ALMA telescope in Chile, we see that at the interior of the dust emission, we have gas emission inside the gap. In blue, we have the emission of CO, and close to the center, where we have high densities, we want to see the emission of another molecule that is HCO+. Now, why this detection of gas is important? Because if you have a disk and you put a planet, this planet, if it's a Jupiter mass planet, will open a gap, and the material will flow, the gas will flow from the outer disk to the inner disk. So the more massive is the planet, the bigger is the gap. And if you have several planets, this gap will be even larger. So the detection of the gaps and the detection of the gas inside these gaps is telling us that probably that is related to the presence of planets. So if I come back to the ALMA image, we think that probably that we are seeing here are the streams of gas that are coming from the outer disk to the inner disk through two planets that are present. Very exciting, very interesting. The presence of the planet in the disk will also change the density profile, and we will have spiral waves. And these spiral waves is exactly that we start to observe with in near-infrared observations. And this is an image taken with the Subaru telescope where we see these spiral patterns. This is all beautiful. The presence of gas inside the gaps, the presence of the spiral patterns are all consistent with the presence of planets in those disks. However, this is not the only explanation possible, and we must be a little bit careful. The real evidence for the presence of planets will be the direct detection of them in these disks, and we will be able to do that in the following years with the new instrumentation that we will have, for example, at ESO.